Okay, folks. Welcome back. Folks, glad to be back on campus. I'm glad to have you all back on campus. It gets very quiet here over the summer. It's always nice when things reanimate. I'm going to talk a lot more about this later on in the lecture. This is a little sneak peek of Lab 2 for everybody. But before I do that, I want to go over some first day of class administrative things. Let me share my screen here. So this is ECE 4760 or 5730, depending if you're a master's student, which is Digital Systems Design using Microcontrollers. The course website is listed here. You're welcome to write it down if you want to. If you Google ECE 4760 and scroll down a little bit, it's pretty easy to find as well. At this site, you will find all the information that you need about how to contact me, where to find me on campus. That said, I'm an easy guy to find. I am pretty much always in one of two places on campus. I'll either be in Phillips 238, which is the lab where we'll all be working together this semester, or I'm in Phillips 208, which is my office. If I'm not in either of those two places, I'm probably meeting with a student or hiding for a little bit to eat lunch or something like that. In any case, I'll be back probably shortly to one of those two places. And at that site, too, you will find all of the information about this course. So you'll find information about all of your laboratory assignments. I'm going to talk about those lab assignments today as well as a whole bunch of documentation. Some of that documentation is from Raspberry Pi, which is the company that makes the microcontroller that we're using this semester. Other of that documentation is generated by me for this course. So you'll spend a lot of time perusing this website. You might want to look through it a little bit. What I want to talk about today, my goal for today, where's my cursor, is to the best of my ability answer the following three questions. What's the structure of this class? What hardware are we going to be using in this class? And what are we going to build with that hardware? The reason I want to spend a whole lecture talking through this stuff is, as some of you are aware, there's a lot that's new about this class this semester. There's a lot that stayed the same. The course structure in particular is the same as it's always been, and I'll talk through exactly what that is. But almost every technical aspect of this class has been updated this semester. So we have a new microcontroller. In years previous, we've been using the PIC32. This year, for the first time ever, we're using the RP2040, which is the first microcontroller created by the Raspberry Pi company. A new microcontroller suggests all new documentation. So that means all new data sheets from Raspberry Pi, as well as all new course documentation, which is all found on that website. There's a whole new website. All the labs are new, which is cool. I think the labs are really cool. I hope that you'll find them cool as well. There's new PCs in the lab. That was just a coincidence, but it's just everything's new. Literally everything is new. So I want to spend some time clarifying precisely what it is that you've signed up for this semester, and hopefully to get you excited about it. I want to talk a little bit about the microcontroller that we'll be using, this RP2040. In Wednesday's lecture and on Friday's lecture, I'm going to do a pretty thorough hardware-software overview of the RP2040, but I just want to introduce it today and talk a little bit through some of the bells and whistles that it contains. And then what I want to spend the most of today's lecture discussing is what you're going to build this semester. This is a building class. We're going to be building stuff, and I want to talk through the stuff that we're going to be building. So let me start with the stuff that stayed the same. Sure, Brian can come in. The stuff that has stayed the same this semester is the structure of this course. As many of you are aware, this is a hardcore laboratory and design class. So the course is composed of 3 laboratory assignments. Each of those laboratory assignments lasts 3 weeks. And in each of those lab assignments, I'll ask for you to build something. We'll talk through what those things are, but the first thing that you'll build is audio related. You're going to build a synthesizer and then something that listens to audio and responds in response to what it hears. The second one's going to be computer graphics related. We'll talk about that. And the third one's going to be robotics related. Each of those lab assignments is going to culminate with you demoing the thing that you built. You'll demonstrate it to me, you'll demonstrate it to the TAs, and you'll prove to us that it has met the specifications that we've laid out in the lab write-ups. There's going to be a laboratory assignment, or I'm sorry, a laboratory report associated with each lab assignment. You can find information about what those lab reports should contain on the course site. They contain all the stuff that you would expect to find in a lab report, basically. There's a bunch of content that's going to be the same for each lab report, and then for each assignment, there's going to be some assignment-specific stuff that we ask for you to also include in that report. I'm going to talk through precisely the thought process that goes into these lab assignments, but among other criteria, one of the things that these lab assignments aims to do is add some additional tools to your tool belt, so that by the time you finish the third, you'll have experience with a whole bunch of different algorithms. You will have been exposed to most of the hardware peripherals on the RP2040 microcontroller, and you will have been asked to use you'll have been exposed to and implemented a bunch of optimization techniques for making your code run faster, that kind of thing. So that by the time you finish the third, you have all these tools in your tool belt, and you'll be asked to propose a design project, and the whole last 4 weeks of the course is you get to build whatever you want to build, subject to a few constraints that I'll talk about, with flamethrowers, that kind of thing. But you'll get to build whatever you want to build in those last 4 weeks. There are no tests in this class. There's no graded homework. The only deliverable that you turn in is those lab reports, and then for your final project, you will create a website instead of a laboratory report. And if we have time today, I'll show you some of the previous projects from previous semesters. They're wildly diverse. What else to say about this? I will just say one slight word of caution about this no homeworks thing. There's no homework that you turn in. That does not mean that there's not out-of-class work associated with this class. I like to just gently remind folks of this because every now and then there's a little bit of confusion about it. But just remember that this is a 4-credit class. The rule of thumb here at Cornell is you should expect about 4 to 5 hours of work per week per credit hour. So for this class, you should expect something in the neighborhood of like 16 to 20 hours of work per week, including these lectures and including your scheduled lab sections. But you add that up and you can say, okay, we're in lecture for 3 hours a week. You're going to be in your scheduled lab for about 3 hours a week. On average, maybe you're working on lab reports 2-ish hours a week. Where's the rest of that time come from? The answer is it comes from preparing for the lab sections. So for each lab, there's a whole lot of reading. And these labs are scoped in complexity to be, how to put this? They are complex enough that it's impossible for me to hold the whole system in my head, right? In order to implement this stuff, I have to actually like think about the code I'm going to architect, draw out state machines, think about how I'm going to arrange things, what circuits am I going to build to help bring this project to reality. You'll have to do that also. So each of your lab sections is 3 hours long. In order to complete the lab in that amount of time, you'll have to put in work outside of class, right? So there's no homework. There is homework, kind of. You have to prepare for the lab sections, okay? And then, like I mentioned, a 4-week, totally open-ended final design project. You are free to build anything that you would like that is legal and that is within reason. Legal, I hope, is self-evident. Within reason, I'm going to ask for folks to propose a project. So as we get near final project season, you'll submit a 1-page summary of here's what I'd like to build. Within reason just means that you're not proposing like a PhD dissertation, which sometimes happens. It can be difficult to scope the complexity of these things, but sometimes someone proposes something, you go, let's dial that back a little bit. And likewise, we don't want to see stuff that's too easy. So we help you get this into the right scope. And then, of course, nothing that's going to endanger you or the other people or burn down the building or anything like that. So like I said, no flamethrowers. Oh my God, I saw a video last week of, maybe some of you saw this. I saw it on Hackaday, I think. This guy that built a device that would throw throwing knives with incredible accuracy. Really cool. Not appropriate for this class, right? So that's what I kind of mean by within reason. So in the past, we've seen lots of robots, lots of musical synthesizers, emulations of Enigma machines, fractal generators, all kinds of stuff. We'll brainstorm lots of ideas. And then, like I said, you'll create a web page associated with that project. Any questions about course structure? Okay, we will have lab this week, incidentally. I'll mention that also. So if you're in the Wednesday lab section, we'll have lab on Wednesday. Okay, so let me just briefly introduce the microcontroller that we're going to be using this semester. Like I said, we're going to spend the rest of the week really sort of thoroughly stepping through all the stuff that's in this thing. But just to introduce you, we're going to be using the RP2040, which is this microcontroller, on the Raspberry Pi Pico, which is the development board that Raspberry Pi has put together to host this RP2040. And it contains a whole bunch of cool features and hardware peripherals. And throughout the semester, you're going to get exposed to pretty much all of these. And if you don't recognize some of these acronyms just yet, we'll go over all this stuff in class. But let me just briefly walk through these things. First of all, within the RP2040, there are 2 ARM Cortex-M0 cores. It's a dual-core microcontroller, which is new for this class, and which is kind of cool because it allows for us to discuss parallelism. It allows for us to discuss safe execution of code between cores and communication between cores. You're gonna really exploit these dual cores in Lab 2, which is an optimization lab that we'll talk about. 12 DMA channels. DMA stands for direct memory access. These are simple coprocessors that you can program to move data from one place in memory to another place in memory with no CPU interaction. And I say that, and depending on your level of experience with microcontrollers, you might say, sounds kind of boring, who cares? The power in this is that all these other hardware peripherals are memory mapped. So that is to say, this ADC, when you sample the analog to digital converter, that sample goes to a place in memory with an address. You could, for instance, configure a DMA channel to automatically, with no CPU interaction, go grab that ADC sample and move it to some buffer where you're going to run an algorithm on it, or perhaps you move it to the place in memory where the SPI channel is looking for information to transmit. So you could set up a system that, for instance, you could have an ADC sample a microphone, and then you could have a DMA channel automatically move that sampled data from the ADC sample register over to the SPI transmit register. Maybe that SPI channel is communicating with a DAC that's going out to a speaker. You could have full audio loopback with no CPU interaction, right? So it's a really powerful mechanism for offloading tasks from the CPU into these background processes. A bunch of serializer deserializers, 2 UART channels, 2 SPI channels, 2 I2C channels. We'll use an example of each of these. 16 pulse width modulation channels. We'll use those in Lab 3. A USB 1.1 controller. Haven't played with this yet, actually. Maybe one of you will. I'll state that one of the exciting things about being a student in this class this semester is this microcontroller came out in January of 2021. And since then, I've been playing with it, kind of obsessed with it. I've been playing with it pretty much nonstop since then. So if you add up all that hours, that's a lot of hours. That's hopefully enough for me to stand up here and not look like an idiot. That said, these are complicated systems. I haven't explored every nook and cranny of this microcontroller, but experience shows that it's about the right time actually to teach a class with this device to students like you all, because you can teach me also. So if in this class you do a final project that uses a feature on here that I don't have a bunch of documentation about yet, and you make nice documentation for it, that documentation that you generate will permanently become a part of the course materials, and you'll be credited with that forever. Yeah?
I saw the USB 1.1 controller is used to emulate a USB connection between the computer so that you can flash your code onto the...
It is, yeah, that is one of the uses for it. You can also do custom things with it. But I'll talk about the programming process for these things, and it is pretty unique as far as microcontrollers go. As I'll demonstrate, the way that you program these devices is there's a little button on here called boot select. You push the button and plug it in, and the microcontroller appears on the PC or your laptop as an external memory device, like a flash drive, and you drag and drop the executable file onto it, and it's programmed. Pretty unique. But in any case, yeah, we'll talk about that. There's 30 GPIO pins. There's a 12-bit ADC. It's an effective number of bits of, I think, like 8.7. with a 5-input mux, which is to say you can map that ADC to 4 of the GPIO pins. The 5th input to that mux goes to an internal temperature sensor. So you can use the ADC to sample internal temperature. These are totally unique to the RP2040. We'll spend some time talking about these. 8 PIO state machines, programmable input-output state machines. These are coprocessors, so processors that are separate from the ARM Cortex-M0s that live inside the RP2040 that you can write programs for. The programs that you write for these PIO state machines, you write in assembler, a custom assembly language called PIO assembly. It includes 9 instructions. I won't ask you to do much of that. You're going to use PIO programs to do things like drive a VGA screen. They're incredibly powerful for building custom high-speed communication interfaces from the RP2040 to some other device. For example, a VGA screen, which some of you may know requires a 25 megahertz clock, right? So that's a fast interface, and these PIO state machines allow for you to build that so that the RP2040 can communicate to a VGA, which makes our computer graphics experiments really fun, incidentally. In years previous, we've used the small SPI TFT displays, which are cool, but now we get so much pixel real estate, gorgeous 640 by 480 VGA screen. So in any case, we'll talk about these a bit. They're a little niche, perhaps, but they're cool enough that you'll have to indulge me at least a couple lectures talking about how interesting these things are. And then there's some hardware that's optimized for specific operations. For example, there's an 8-cycle integer divider. So there's hardware in the RP2040 that has been designed and optimized to speed up divide operations. Those of you that have tried to write optimized microcontroller code know that the divide operation kills you, right? It costs you so many cycles. The divide here is relatively cheap. Again, in lab 2, which is an optimization lab, you're going to really enjoy that. There's an optimized interpolator. I'll be honest, I haven't found a great use case for this yet. One of you might in your final projects. I haven't really been able to find a good use case just yet. I'm sure they exist. 264 kilobytes of on-chip SRAM, and then a QSPI interface to external flash. When you load a program onto the RP2040, you actually load it onto an external flash memory device. And then there's an execute in place capability that the RP2040 has that allows for it to run code that lives on external flash. That flash communicates over this QSPI channel to some cache that lives on the RP2040 so that it can execute. It executes that code, but the code lives on external flash. So like I said, the next couple of lectures, we're going to really take a tour of this thing. But in short, those are all the sorts of bells and whistles that you're going to get to play with this semester. And of course, this probably goes without saying, but the fun design challenge with these is all these can talk to the other things, right? So you can have the DMA channel talk to the ADC and talk to SPI. You can have DMA talk to PIO. So it's a fun design problem, right? To figure out how exactly you're going to connect all these different hardware peripherals to achieve some goal. Questions about this? Okay. So then what I want to do is show you the lab exercises that you're going to be conducting this semester. Before I do, I want to just really briefly talk. So no lab exercise is perfect, right? But each one is designed to attempt to meet the following objectives. And I want to just walk you through the objectives that I'm trying to meet with each of these laboratory assignments so that when I describe each laboratory assignment, you might have some context for why it is what it is, right? So, because it's a harder problem than you realize, actually. I didn't realize this when I was a student. It's hard to come up with a lab assignment for a class like this. But each one aims to be self-motivating, which is to say that in each of these laboratory assignments, I'm going to ask you to build something that is interesting, I think, in its own right. So separate from the techniques that are required in order to actually build it, separate from the interesting hardware peripherals that are involved in making it work, the thing itself, just the toy, the tool, the device that you end up with, I want for that thing to be interesting. That's for a couple of reasons. One of them is, one of the things that I really attempt to do in this class, particularly in the laboratories for this class, is to try to nurture an environment of play. Ideally, what I would love is for when you all are working on these projects in the lab, for you to feel like you're playing and tinkering as opposed to working. And there are a couple reasons that I try to make that happen. One is you learn a whole lot better when you're playing, right? And the other reason is you're happier. And actually that does matter to me, right? I do actually want you to be happy and to enjoy doing this stuff. For me, in order for me to feel like I am playing as opposed to working, I need to be building something that I think is just cool in its own right. So that maybe I'm not particularly, maybe some of you will be motivated by the algorithms and the techniques and all this stuff, but even if you're not, I hope that you're motivated by just wanting to have the thing at the end because it's interesting, right? That's the goal. Each lab is designed also to be extensible. Every year, for every lab, there's a handful of students that gets obsessed with that particular lab. And if you are one of those students and you get obsessed with lab 1 or lab 2 or lab 3, I want for there to be interesting places for you to run with it, right? So as I describe these labs, I'll talk to a little bit about the ways in which you might take these things and run with them to some pretty interesting places. Each lab, and I would say more so the collection of labs that compose this course, aims to appeal to students with a variety of interests. The electrical and computer engineering department here at Cornell is broad, right? So there are people in this room, in all likelihood, that are really interested in digital signal processing. Some of you might be really interested in audio synthesis. Some of you might be really interested in computer graphics. Others of you might be really interested in analog stuff or robotics or whatever it may be. So what I aim to do with this collection of labs is have a little something for everybody. And the other thing I'm hoping to do is, say you are really into computer graphics and you're not that keen on audio synthesis, I want to present audio synthesis in its best light, right? So I want to ask you to synthesize some audio that's interesting enough that you go, oh, well, maybe this is kind of actually more interesting than I thought it was. Obviously, each lab is designed to add tools to your tool belt. That is to say that each lab will expose you to a new set of hardware peripherals in the RP2040, a new collection of algorithms, some new set of optimization techniques, so that you were adding to the stuff that you know with every lab. I think that probably goes without saying. The challenge I would say with this one is it kind of couples with the first one, where everything that we add to the lab, I'm never going to ask you to use a hardware peripheral just because I want you to learn it, right? So the challenge is to design these things such that if I'm trying to teach you, say, DMA, in order to actually get the thing to work, using a DMA channel is a critical part of that design, right? There's no getting around it. And that's true of the algorithms and stuff as well. They're critical aspects to actually getting the thing to work. This one, it sounds a little dramatic. The more you get to know me, well, you'll come to expect these things. But in any case, when possible, sometimes a particular laboratory exercise can fundamentally change the way that you perceive the world in some way. And when that happens, you never, ever forget the content of that lab. So I'll give you an example of this. Last semester, for our audio synthesis lab, I asked the students to synthesize bird songs. Specifically, we synthesized the songs of northern cardinals. Anybody here like birds? The northern cardinals are the pretty red songbirds. You see them around campus all the time. Songbirds are, this is a very brief aside, songbirds are really interesting because their songs are almost pure tones. So that is to say, if you were to look at the audio spectrogram of a songbird's song, at any particular moment in time, they're really only singing one frequency, but then of course they modulate that frequency over time to generate the complicated song. The algorithm that we're going to use in this class to synthesize audio, it's an algorithm called direct digital synthesis. It allows for you to synthesize a target frequency with shocking accuracy, and then you can modulate that frequency. So, you map the frequency sweeps you see in the audio spectrogram to mathematical functions. You implement those to describe the changes in frequency over time, and you can generate simulations of birdsong that are good enough to trick the birds, You can take this system outside and play it, and a bunch of territorial cardinals show up and start yelling at you. But what's interesting about doing a project like this is you build something like this, and suddenly you hear birds singing. And of course, you all already hear birds singing, but right now you walk across campus and birds are singing, and it's background noise, right? It's just the stuff that's going on. But when you do something like this, suddenly you really hear them. You hear a particular bird and you start thinking, oh, could I synthesize that? And you start trying to map the frequencies. It fundamentally changes the way that you experience birdsong. This semester, we're going to do a different animal. We're not doing birds. I'll show you in a second. Another one is, in lab 2, you're going to implement a flocking algorithm called Boids. I had it running up here on the screen at the beginning of the lecture. That too, I asked folks to do this the past couple of years, and after it was done, I would get tons of emails from students with cell phone videos of starlings over Ithaca, or fish in BB Lake, or bugs, because as soon as you implement this thing once, everywhere you look, there's this algorithm running, right? It fundamentally changes the way that you perceive these things. So when possible, I like projects that do that. So you'll see that reflected in the labs. This semester in particular, so a lot of you in this room are seniors, which means you're on your way out of here. Sad, I know. A lot of you are master's students, which means you've just arrived and you're also almost out of here. Some of you are juniors. You have a little more time, but not much more time. So the other thing that these labs aim to do is to be sort of a technical homage to your time here at Cornell. And the way that we're going to do that is each lab draws upon or is inspired by or is somehow related to research that's going on here at Cornell in other departments. So when I describe each lab, I'll describe the Cornell connection. But we're doing labs this semester that connect with stuff that's happening in applied math, neurobiology and behavior, and mechanical engineering, aerospace engineering. And this last one is so much more important than you guys realize as students. A big reason these labs are what they are is I think they're interesting. That's a huge reason. If I find the stuff that we're doing fascinating, it makes it so much easier for me to teach it. It makes it so much more fun for me to teach it. And hopefully, if I'm having fun, it's a little bit more fun to be in the class, right? So you'll see a lot of that. Okay, so let me show you the labs. In order to do that, I have to program this device. So, one moment. Okay. People recognize what animal that is? Cricket. Bonus points for this one. Not really, but a firm handshake. Does anyone know specifically what species of cricket that is? Okay. No entomologists in the room. That's okay. So that is a snowy tree cricket. I have chosen to synthesize the snowy tree cricket for a few reasons. One is it's native to Ithaca. So if you are walking home on campus in the evening and you're walking past woods, pay attention. You're going to hear that sound, and it's snowy tree crickets. The other thing that's interesting about them is they do something that is fascinating and more common than you might think in nature, which is they synchronize with each other. So if you sit and you listen for a while, you're going to hear some crickets. And after a little while, you might notice that you're actually hearing lots of crickets, and they're all chirping in sync. And you see this synchronization occur elsewhere in nature too. For example, you see it in fireflies. In the Great Smoky Mountains in Tennessee, every year, there's a few weeks where the fireflies all synchronize. If you are trying to get a campsite to go watch that, you have to do it like 2 years in advance. It's really dramatic. Everybody wants to go see it. You also see it in certain cells, pacemaker cells in the heart. You see it in certain cells in the brain. The algorithm that describes that synchronization behavior is one that was famously studied and subsequently understood by a professor here at Cornell, Steve Strogatz. Anybody here take nonlinear dynamics and chaos? Yeah. So Professor Strogatz very famously researched and discovered the algorithm that describes these synchronization events in nature. What you will be tasked with doing, this lab occurs in 3 phases. The first thing that you're going to be asked to do, by the end of next week actually, is get that to work. You have to synthesize cricket chirps. A cricket chirp, as it turns out, is a pure frequency, so it's a sine wave of one frequency. It modulates on and off a bunch of times. So each cricket chirp is composed of a bunch of syllables. So it's like chirp, 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 a little gap, chirp, 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 a little gap. If you get the frequency right and you get the timing right, your brain goes, that's a cricket, right? The illusion happens. The first thing that you'll be asked to do is get that sound to work. Once you get that to work, the second thing that you will be asked to do is plug a microphone into the RP2040, into the microcontroller, and use that microphone to detect other crickets. How are you going to do that? You have to implement an FFT algorithm on the microcontroller. You know the chirp frequency of other crickets. You look for power in that FFT in the particular bin associated with the cricket chirp frequencies. And when you see it, you say, that's a cricket. So that's phase 2. Phase 1 is synthesize a cricket chirp. Phase 2 is detect other crickets. Phase 3 in the third week of the lab is take an action when you hear another cricket. And the action that you take is described by Professor Strogatz's algorithm. So that you hear another cricket, you adjust the amount of time until when you chirp again in such a way that over a little bit of time, you synchronize with the other cricket and the other cricket synchronizes with you. There is no leader in this algorithm, incidentally. No one is setting the pace. Everybody is adjusting to everybody else, and over time, the synchronization event occurs. And then the fun thing that we're going to try, is this going to work? I have no idea. The fun thing that we're going to try then is once everybody has unit tested their own system, their own 2 crickets, the last step of this is to attempt class-wide synchronization. So what we'll try to do is synchronize everyone's artificial cricket in the lab. I don't know if that's going to work or not, but it's going to be fun to try. Okay. The second lab, this one, because I have it already programmed, I actually can show you this. So the second lab that we're going to do is implement this algorithm. Does anybody know the name of this algorithm? Boids. Yeah, someone said it. It's Boids, which is it's short for bird-oid object. This is an algorithm that was developed by a man named Craig Reynolds in the 1980s. I think it was 1984. But it's an artificial life program. And as you can see, it's a program which generates unbelievably realistic simulations of flocking behavior. And what's interesting about this is the algorithm, there's a series of knobs that you can turn that adjust the behavior of the flock. As I have the knobs turned right now, this to me kind of looks like birds, maybe. Maybe some of you see fish, okay? But what's interesting is you turn the knobs a little bit and your brain is saying birds, 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 then you turn a little bit more. And for reasons that are really difficult to articulate, the brain goes, that's fish now. And then you turn a little bit more and you go, oh, it's bugs now. And then you turn them a little bit more and the whole illusion falls apart. So this too is a lab that occurs in phases. One aspect of this lab is the animation that you're watching right here is running at 30 frames a second. And that is a strict deadline that I enforce. 30 frames a second gives this nice, smooth, organic looking behavior, right? So your program, your animation, will have to animate at 30 frames a second. So that means you have a certain amount of cycles to spend. Your challenge is at 30 frames a second, animate the largest swarm that you can. Every additional member of this flock requires additional computation. Eventually, you run out of time, right? You can no longer meet the timing deadline. There's going to be some friendly competition here. The winning group is the one that animates the largest swarm at 30 frames a second. This is 700. In order to do this, people get obsessed with this. So in order to do this, you are going to have to think about optimizing your arithmetic. Floating point isn't going to fly here, too slow. So we're going to talk about an alternative called fixed point, which allows for you to use integer arithmetic, which is way faster than floating point arithmetic, but to maintain fractional resolution. We'll talk a lot about this. You are going to have to think carefully about, you're going to have to look at the algorithm pretty carefully and think, is there a way that I can parallelize this across 2 cores? There is. But it's not trivial. And then once you parallelize it across two cores, do those cores need to synchronize? At what point do the two cores need to sync up before they move on to the next parallel phase? You're going to have to think about loop unrolling. Each Boid is looking at every other Boid here. Is there a fast way to do that and a slow way to do that? There is, yeah.
What happens if we win the competition?
What happens if you win the competition? I haven't decided yet. I'm open to suggestion. Maybe, I don't know, there's certainly the glory of victory. And then there will be something else too. I'm not exactly sure what it's going to be. Okay, but this isn't all we're doing with this lab. The other thing that we're going to do is, hold on. Okay, so right now, what these lines are showing is these are the points at which the Boids start to turn around. So this is sort of the boundary that they're flying around in. You are going to implement a user interface that allows for you to change this. So for instance, oops. So now there's top-bottom wrapping. Boids that fly out the top fly in the bottom. And they're being constrained to go in this sort of, up this road here, right? The reason that we're doing this is on top of implementing the Boids algorithm itself, you're going to be asked to implement an algorithm on top of that algorithm. And the particular algorithm that you're going to be asked to implement is one that was discovered by, discovered by, I would say, another professor here at Cornell named Tom Seeley. He's a professor emeritus in neurobiology and behavior who studies bees. Are you all aware that this is the world's preeminent bee research institution? Maybe that's arguable, but if it's not the world's preeminent bee research institution, it is certainly in the conversation. In any case, what Professor Seeley was studying is there's this thing that happens when a colony of bees gets too large, which is that it needs to separate, right? Once the colony gets beyond a tenable number, it needs to divide into two colonies. The process by which that happens is called swarming. And in particular, what happens is half the colony leaves and they come to rest on some sort of a nearby structure. Usually it's like a tree branch or something like that. And they sit there and most of the colony just hangs out and conserves energy. And then there might be 10,000 of these of members of this leaving colony, incidentally. And then a shockingly small number of bees, the scout bees, go out and look for a new place for them to go permanently reside, a new hive location. So the scout bees go out, they find candidate locations, they come back, they report the locations of those candidate hive sites to the other scouts in the hive, so that the scouts go and check out each other's locations, and they vote for their favorite by hanging out at that location for an extended period of time. The scouts all have some internal model for the number of scouts that there are. So when they get to a candidate site and they look around and they realize, oh, there's a lot of us here, they come to realize that they've made a decision. They go back and they instigate the whole colony to take off, and they lead the colony to the new location. This is fascinating for a few reasons. First of all, the rest of the bees don't know who the scouts are. They don't know who to follow, right? They take off and they just end up going to the candidate location. That's kind of fascinating. The other interesting thing here is it's tempting to assume that take off and go to the new hive site decision only occurs when the scouts reach a consensus. That is, when they all agree. That's not how it works. The colony will take off with disagreeing opinions about where they should go, but even so, they come to a collective consensus about where they're going to end up, and they all go to that candidate location without the colony separating. So the other way of putting that is they leave when they have reached a quorum rather than a consensus, when a sufficient number of scouts is voting for the candidate location, not all the scouts. We're going to animate this in real time. So let me eliminate the boundary entirely. And I'm going to make all the, did that work? Yeah, so now I am biasing the whole collection to this side of the screen. So I've given every Boid a preference in this direction. I can change the direction of their preference and give all the Boids a preference in the opposite direction. But the really interesting thing to do here, let me just reset this. So we're creating a user interface that allows for us to decide upon two things. We can specify how many scouts are in this colony, and we can specify which direction each group of scouts wants to go. So there's scout group A, they want to go this way. There's scout group B, they want to go this way. Each one has a certain amount of preference. We run Professor Seeley's algorithm, and what we'll be able to animate in real time is this collective consensus decision, exactly as it's being made in the real bee, by real bees. And the fun thing that I would like to actually do is then compare our simulated results to his field results and see how well this matches the actual bees. Let me see if I can get this to do something interesting. So let's give us 50 in each group. So it's difficult to see with this lighting, but in fact, each of the scout bees is being colored differently. The ones that want to go this way are colored cyan. The ones that want to go this way are colored magenta. With this setup, you can't see those colors, but they have disagreeing opinions. And what we should see is, despite the fact that there's exactly the same number of scouts that want to go in each direction, well, one of a few things will happen. It may be the case, depending on how we've set the various parameters, that the colony does indeed split. Or it's going to be the case that one group of scouts sort of submits to the other group of scouts and says, okay, we'll go where you want to go. In this case, they're splitting. But we'll play with this, and you'll have the opportunity to sort of play with different weights and different number of scouts, and in real time, animate these collective consensus decisions. So that's lab 2, connection with neurobiology and behavior. Lab 3 is difficult for me to haul across the quad, so I didn't. But what lab 3 is a classic problem in controls, which is balancing an inverted pendulum. We're going to do a little twist on it, where the ordinary way that we balance a pendulum, or the way that this problem is often presented in a class like this, is to balance the pendulum by moving its base. What we're going to do instead is balance the pendulum by moving a reaction wheel on the top of the pendulum. Folks familiar with what a reaction wheel is? Okay, so yeah, this comes from spacecraft engineering. And there's this problem when you build a spacecraft and you put it in space, which is you want for it to point in a certain direction. Let me pull up the lab exercise here. But getting something to point the way that you want it to point when there's nothing to push against is kind of a hard problem, actually. It's a really hard problem. One option is you could use, let me share my screen. One option is that you could use thrusters. Sometimes that's the right answer, but there's a cost to thrusters. In particular, you have to carry the propellant. That weighs a lot. You don't want to do that with spacecraft. The other problem that thrusters can introduce is they tend to be impulsive in nature. Pop, 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 pop. That tends to be what you get out of a thruster. If you're trying to point something like a space telescope really finely, right, an impulsive control input isn't necessarily what you want. It can make doing that impossible for a few reasons. It can kick you off your line of sight. It can also excite modes in the spacecraft so that the whole thing starts kind of wiggling, which if you have sensitive optics pointing at some distant place, you don't want that to happen. So the solution instead is to use momentum control devices. So what a reaction wheel is you take a heavy disk, you rigidly attach it to the spacecraft so that the disk and spacecraft are considered one system. And you could imagine that if you had, say the spacecraft is a cube, there's a disk sitting in the bottom, it's floating in the vacuum of space, and you start spinning the disk clockwise, what's the spacecraft going to do? It spins counterclockwise. It has to conserve momentum, right? So you take one of these and point them in each direction, and you have 3-axis control of the spacecraft. And there are more advanced versions of this sort of technology as well. But fundamentally, this is how pretty much every modern spacecraft controls its orientation, is with these reaction wheels. We're going to use them not to exert a torque on a spacecraft body, but instead to exert a torque on an inverted pendulum to get it to balance. There's a lot going on in this lab. We'll spend a lot of time talking about this. And then, after doing all these things, you'll be asked to do a final project. And I want to talk just briefly about these final projects. As I mentioned, it's entirely open-ended. We've had projects of all sorts of varieties. Lots of audio projects, synthesizers, auto-tunes, bird songs and whale song generators, head transfer functions. Create a device that you plug headphones in and put in earbuds, and it makes it seem like there's sound coming from somewhere. The AirPods are doing this now. This must be a new feature. Maybe folks have realized this, yeah. But you could implement that. Computer graphics lab, networking internet-based projects. I'm open to this. Might require CIT permission, depending on what you want to do. Robotics projects, artistic projects. I'm open to projects of all varieties in this class. And in particular, something for you to think about is throughout your engineering education, engineering has been presented to you as a means of solving problems. And if you want to do a project like that in this class, that's wonderful. I'll be honest, for my own personal projects, it's not my favorite flavor of engineering. The kinds of projects I love are those that use engineering as the mechanism by which I learn about something else. So suppose you're interested in nature or art or history or whales or whatever it may be. One mechanism by which you might learn about that thing is reading. Another mechanism by which you learn about that thing might be video or listening to podcasts. I like using engineering as the mechanism by which I learn about that thing. So I have something I'm curious about. This is how I come up with my own project ideas. I have something I'm curious about, and I try to think up something that by building the thing, I learn about that other thing. It's fun because it makes the engineering process as opposed to the end result. The process is as enjoyable as the end result, which I enjoy. Just to say, so one, if it can be a challenge, right? To be presented with this totally open-ended, build anything you want. What I like to encourage students to do is, if you're not sure what you want to build, one strategy you might consider is make a list of everything you're curious about. You don't have to know anything about it. Just what are you curious about? Russian literature and bugs and whatever, right? Make a big list, and then we'll meet together and try to figure out projects that allow for you to learn about that thing you're curious about. Those tend to be cool projects. Make a separate list of everything you like to do outside of engineering. Do you like playing video games? We had one group last semester that liked playing those fighting video games. They have complicated control inputs, apparently, I've come to learn. So they built a system that allowed for them to cheat, where they could use the microcontroller to record a whole sequence of control inputs, and then push a button, and the microcontroller would spoof the keyboard to replay those control inputs. So if they got it right once, they could get it right every single time. And it works beautifully. Do you like bicycle riding? Come up with a project that augments that. We'll talk a lot about project ideas, but it's good to just get your wheels turning now, right? Just start thinking about this a little bit. Okay, we're out of time. So as I mentioned, lab this week. So I'll see you all in lab on Wednesday, Thursday, or Friday.